circle, it is not that all the time there has to be some string tied to that body. There could be cases like, let's say this is a hemispherical surface, this is O and radius is R, and over here a small mass m is released over here. Then someone asks, that is, and it is a frictionless surface. Then it is asked, that is, when it reaches over here, this block is over here, obviously it will oscillate like this, it will reach this height, once again it will keep on oscillating. It is asked, when this block of mass m reaches this, the bottommost position, then obviously it shall be pushing the this surface downwards, all the time it shall be pushing the surface downwards. Then what is normal reaction at that moment, at this moment? So over here what we do is, first of all, suppose this is R, so we can also find, that is, from here P plus Ke over here is equal to P plus Ke over here. That is, we can find, using conservation of mechanical energy principle, we can find the velocity over here or speed over here. Once we find the velocity over here, then certainly centripetal acceleration can also be calculated. That is, V square upon R can be calculated. Then over there, what is the demand of the centripetal force? That can also be calculated. That is, Fc is equal to mv square upon R. Now we look out the forces, the real forces which will meet this requirement. Now what are the real forces? One is, if we draw the free body diagram of this, then this body mg is acting in this direction. This will push this surface downwards, let's say with the force N, and this will once again retort back with the force N. To every action there is equal and opposite reaction. Similarly for earth also, earth is pulling it down with the force mg. This block will also pull the earth in the upward direction with the same force mg. To every action there is equal and opposite reaction. To every action there is equal and opposite reaction. Action, reaction, they are always on two different bodies. So onto this block of mass m, if we see that we have two forces, one is N is acting this way, the other is mg is acting this way. Eventually this block, it has to accelerate towards the center. It means the net force has to be towards the center. It means N has to be greater than mg. So N minus mg, this is the net force, and this should meet the requirement, that is mv square upon R. So from V we have calculated, G etc., M we know, R we know, so from here N can be calculated. If you have to find the case over here, it is similar like when a string was tied to this, it is same. So N is here, N will be in this direction. So using the conservation of mechanical energy principle, you can find the velocity over here. So once that is found, N is in this direction, suppose this angle is theta, so obviously this angle is also theta. So mg is in this direction. Break the mg into components. You will not make the components of normal reaction because that is already aligned along the radius. Break the components of mg. One is along the radius, the other is tangent to this circle. So if this is theta, this and this two lines, vertically opposite lines, vertically opposite angle, so this is theta. So this is mg cos theta and this is mg sin theta. Now the same case like what we had done in the when the body was tied to a string, over there it was tension and over here it is normal reaction. So once again, if it is centripetal acceleration over here is, using the conservation of mechanical energy principle, you can find the V over here. So once V is calculated, V square upon R is calculated, centripetal force is calculated, mv square upon R, this is calculated for this point, then N is here, mg cos theta is here, so equation comes out to be N minus mg cos theta. These are the two real forces which meet the requirement mv square upon R. And this force mg sin theta, it is going this way, it will pull it this way, and as a result its speed will be reducing when it is going up. We had a hemispherical surface. Now we had once again a hemispherical surface, but it is like this, where the body right now it has a speed v or velocity v. At this angle theta, radius is r of this circular surface. All the surfaces, they are frictionless, and right now we are asked what is the normal reaction. At this instant, if it is given, that is, it is in touch with this surface, then obviously there is some normal reaction. Normal reaction will be in this direction and mg is acting in this direction. When v is given, it means centripetal acceleration is also given, v square upon r. It means centripetal force can also be calculated, that is mv square upon r. If this can be calculated, now we come to what are the real forces which are able to meet the demand, that is mv square upon r, because this is moving in a circle. If it is moving in a circle, it means there is centripetal action, there has to be a net centripetal force which is of value mv square upon r, and to meet this requirement there has to be some forces, be a single force or be 10 forces, but there has to be a net force mv square upon r towards the center. Now we see one is normal reaction that is already aligned along the radius, so will not break into components. mg is not aligned along the radius, so mg is going to get broken. So this and this line, they are parallel, this is angle theta, so if this angle is theta, so this is also angle theta. If this is mg, once again we take this triangle, so this is going to be, this side is going to be mg cos theta, and this is going to be mg sin theta. Now along the radius we have two forces, one is n this way, the other is mg cos theta this way. Ultimately the net force has to be toward the center. So it means mg cos theta minus n, this is this way, net force has to be towards center. These forces are in opposite direction, so mg cos theta minus n. What I do is mv square upon r, this meets the requirement of centripetal force. And this is force tangential, this is tangential force mg sin theta. Because of this there is going to be tangential accretion. Now there's one interesting thing to be seen over here. Let's say when a car is moving over speed breaker, as the speed is increasing, at times it happens is that this car loses contact with the surface. How it loses is, if the velocity is increasing, suppose this requirement is 100 Newton, suppose this is 100 Newton. mg cos theta, suppose it is 150 Newton. So normal reaction, that is how it will pushing this surface, or this surface is pushing it up, is 50 Newton only. So obviously it is 50 Newton. 150 minus 50, 100 Newton. Now the driver of this car increases the speed, increases the velocity. He takes it to 120 Newton. If he takes to 120 Newton, at this angle, mg is cos theta, this everything is constant. So next time, at the same angle theta, the same driver with the same car, when he was navigating this circle or speed breaker, now he has increased the speed so that mv square upon r requirement, instead of 100 Newton, it is 120 Newton. But mg cos theta, theta is same, mg is same, so this will remain as 150 Newton. So it is only the normal reaction, that is how this car is pushing the surface, or how this surface is pushing it in this direction, that can only change. So this adjusts itself to 150 minus 30 Newton is going to be 120 Newton. Now next time, this driver at the same place, at the same theta, he increases the speed. As a result, the requirement comes out to be 150 Newton. When this comes out to 150 Newton, mg cos theta alone can apply 150 Newton. So as a result, this normal reaction will come out to be 0. So it means when the normal reaction is equal to 0, it means at this instant, this car will just be in touch or just lose contact with the surface. Normal reaction has become equal to 0. That is, the bodies, they are not in contact with each other, or the bodies, they are just in contact with each other. That is, at this instant, when this is 150, this is also 150, we'll say that is, this is just in contact with this surface, or this has just lost the contact with the surface.